Welcome everybody, my name is Andreas Maier and I'm hosting the Pattern Recognition Symposium. Today I have an online presentation for you by Florian Kordon and it's entitled Contour-Based Bone Axis Detection for X-ray Guided Surgery on the Knee. Florian, looking very much forward to your presentation.
Thank you very much for the introduction. I'm going to present you a new approach for the detection of the anatomical axes of long bones on 2D X-ray images. In particular, we are interested on intraoperative X-ray images. And as you can see, for example, here already on the intro slide, here these are the axes we are actually interested in. Currently, in this instance of our research, we were performing our evaluations on the knee joint, but we are also planning to extend it to further anatomies, as you can see here on the right. So when we talk about intraoperative X-ray data, they are actually one of the key modalities for trauma surgery and orthopedic surgery. And for these types of surgeries, since they are usually very complex, some manual surgery planning is needed, which is done either preoperatively or during the surgery itself. And of course, the surgery results is usually verified, and for that, usually an X-ray image is used. But right now, this is done usually manually by the surgeon itself. So this is rather complex, time-consuming, prone to errors, and also forces the surgeon to leave his sterile environment to interact with the planning software. So there's actually a quite huge need for some semi-automatic or even automatic guidance solution. And examples for that would be solutions to aid the surgeon when performing reconstructions of ruptured ligaments, or for example, in the reduction of fractures, or if you insert some hardware to stabilize some anatomy, for example, some intermedullary nails into bones. So when we're talking about these planning and guidance tools and also the methodologies behind, they usually work upon a different or a broad set of different anatomical features. So for example, as you can see here, we have different anatomical landmarks. We have reference lines, which, for example, follow a certain bone contour. We have a complete segmentation masks of certain areas. We have some region of interest. And also a very important thing is the anatomical axis. And that's what we are going to focus here today. I brought some examples where this anatomical axis is actually used. So for example, if you look at the wrist, there you usually have to evaluate the axis when you do some fracture reduction to maintain the correct angle measurements. For example, here the inclination angles after, for example, the wrist is broken here. Then another application is, for example, the detection of the Baumann angle at the elbow joint, which is also directly conditioned to the bone axis of the humerus bone. And last but not least, besides many other applications, you have, for example, the knee joint, where here a drilling path is planned with respect to the anatomical bone axis. So current solutions for detecting the anatomical axis usually work on very standardized images preoperatively, but in an intraoperative setting with mobile C-arm X-ray images, usually images of these target anatomies suffer from different truncation levels of the bone, so we cannot assume that the shaft area for which we detect this axis is always the same, and also our target anatomy is rotated and configured in arbitrary fashion. So usually the current methodologies to estimate the axis are not very feasible for this data corpus. So what we were trying to do is to develop a simple and flexible algorithm that is working for different views as well as for different anatomies, so that we can extend it to, for example, also the wrist, and that is also approximately invariant to the target rotation and truncation of the anatomy. So we came up with the following idea. In the first step, we want to detect only the relevant regions of the bone shaft, and especially the bone shaft contour of the bone, which is necessary for the axis detection. And then we take this contour and fit two inscribed circles to these resulting lines. And by constructing a line through the midpoints of these circles, we can actually directly derive the anatomical axis. How do we do this algorithmically? So first we use a neural network to predict our segmentation masks for the bones we are interested in, and also some kind of likelihood encodings for these region of interest. And we do this by fitting some heat maps, which are constructed by using Gaussian PDFs orthogonal to the actual line segment. Then we extract the bone contour by using a logical operation with the original segmentation mask and binary eroded version of this mask. Then we obtain something like this here, which is a 1 pixel border or 1 pixel contour of this bone. In the next step, we actually want to restrict it to the shaft portion we are interested in, and we do this by actually masking the contour we just extracted by these likelihood region of interest encodings. And we then take only these points we are interested in and perform a major axis regression to get some kind of line segment representation. And to then find these midpoints of the inscribed circles is just some basic geometric construction. So the data we wanted to evaluate this approach on, we used 221 clinical X-ray images of the knee joint, and 38 images of these images were also acquired with a standardized measuring field, so that we were able to also provide the measures in millimeter units. The images were acquired as true lateral standard projections, and annotations were provided for the segmentations and also for the lines which then represent the relevant contour regions. The experimental setup was as follows. We first trained the network for the 3 different configurations. So as I told you, we were evaluating it for the knee joint. So we had the femur bone, the tibia bone, and a joint training of both bones. The following results are only for the this last configuration with the joint training, since this performed the best. For the other results, I would like to refer to the actual paper. And then we also performed a clinical evaluation, which is also currently ongoing with some more different experiments. And for the last methodological part, to actually train this bone segmentation region of interest prediction, we used a multitask hourglass network. And the segmentation there was optimized by using binary cross entropy, and this region of interest by using a mean squared error on these heat map representations. Let's go to the results. So first, these are the result and error metrics for comparison to the actual ground truth data. So what we can see here is for the femur and the tibia, very low angulation errors. So it's below 0.2 and 0.35 in the median, and also the maximum values. So the maximal error bound here is super low when compared to the clinical standards, which we see in the next slide. And also the translational displacement of our regressed axis is also pretty marginal for both anatomies. So here are the inter-rater study results, where we compared our automatic solution to 3 different experts, trauma surgeons, who also annotated this bone axis on these images. And also there you can see the inter-rater variance. And as we can see here for the femur, these angular errors are well within the error bounds which are observed for the different experts. If you look at the tibia, which is a little bit more difficult to actually assess the axis for, there we see significantly higher error metrics, especially to expert 3, but also expert 3 is has higher angular errors when compared to the other experts. So we could say that our automatic solution does a pretty good job here in finding a very nice fitting line and anatomical axis, which closely resembles the ones which were annotated by the different experts. And I would like to conclude the talk by following conclusions. The performance of our algorithm is actually pretty encouraging, since we observe very low angular errors, and this is the most important thing, at least from the clinical point of view, and we usually match or even surpass the expert rated performance. And our ROI masking is pretty flexible and can be adopted to many different anatomies, and this also does not impose strong prerequisites on the truncation or the rotation of our anatomy, since we can employ those in our network training. And we are currently, that is one limitation of our approach currently, that we are limited to healthy knees, which means that our approach will fail for knees or bones where you have multi-fragment fractures, which are dislocated to quite a big extent. Right now, we are also evaluating these metrics for different shaft lengths, and for example, also you saw that there is quite a large amount of metal inside the images, so that we also can quantize the error with respect to the amount of overlaid metal. And also, as previously mentioned, we are currently also evaluating this for different anatomical regions, for example, the shoulder region or elbow or wrist region. By that, I would like to conclude this talk and would like to thank you for your attention.